Hi, it is a section 3.23, Adaline, adaptive linear neuron. In Adaline, weights are updated based on linear activation. Here, net input is used against the true label for weight update. So here, phi is the identity function. That means that for activation, here there's no special, no change is applied. So that the net input will be used directly for optimization. The Adaline is particularly interesting because it shows the key concept of minimizing continuous cost functions that lay the groundwork for understanding more advanced algorithms. Continuous cost functions allow the machine learning optimization to incorporate advanced mathematical techniques such as calculus. We'll see details for the algorithm, Adaline. Here we compare perceptron and Adaline. In perceptron, the net input is thresholded and having now value 1 or -1, and these predictions will be used against the true label, and now the weight is updated. Now here in Adaline, the net input and without thresholding will be directly used against the true label for weight update. That's one of the differences. Now we'll see details later on. Here, that is training. Now, when you reach at the prediction stage, then now for this net input, we apply threshold function to get the output. But during the training, without any thresholding, the net input will be used directly. Okay. Here, we'll try to train the Adaline using objective function. One of the key ingredients of supervised machine learning is to define an objective function and to be optimized. And sometimes it's called cost function. Now for Adaline, we can define the cost function J to learn the weight as the sum of square errors. For current weight, we measure the net input, and of course phi is the identity function, and the net input is measure the difference between the true label will be measured. That's error. Now this squared error is summed. That is the objective function for the Adaline. Now for each one here, and we can write this one in detail in this way. That is now yi and minus here w1, x1, and of course over the I, and plus w2, x2i, and so on, so that jth one is wj, now xj, here I, plus last one, if dimension is m, then now that is okay, wm. Now that is wm, xm, and I. Okay, we can write the detail in this way. Once you define the objective function, then now you have to optimize we'll use the gradient descent method, in which now we use minus gradient of the objective function. And okay, before explaining the algorithm, let's consider derivatives. Okay, first we begin with a function as one variable, y called fx. Then you already know that y prime, okay, that is f prime x, that is now slope. From calculus you learned that. Then I want to ask you if it has a direction. What is the direction of slope? What is the direction of derivative? The direction of derivative is increasing direction. Here, if we consider a function like that, increasing and decreasing, and then y prime, f prime, here is the value is positive because slope is positive. If you measure the derivative, then at this point is negative because it's going down. So positive means that direction is this one, negative means that is this one. So that we can say that derivative is increasing direction. Now, for functions of multivariable, you can get gradient. The gradient is now increasing direction. In fact, fastest increasing direction. So minus gradient is fastest decreasing direction. So we try to use minus gradient of the object function and scaled by eta, which is called step length. And now that portion is used as correction term for all the weight, and we are adding now the correction vector of the weight and to get u1. But this correction term is defined involving minus gradient of the object function because it's a decreasing direction. By choosing eta appropriately, now the function value at new w will be smaller than and the value we at earlier w. Okay. Now we try to make practically the gradient. So we make a derivative with respect to wj. Then here, okay, 2 will come out, so cancelled with 1/2, and this term, that is exactly this one. And then now for this part, you have to make a wj derivative. Okay, here wj is appearing here. The coefficient is xji. So this is exactly wj derivative. And if you write down in vector format, then now that is xi, and now minus, so that it disappears, and eta is multiplied, so we can get the correction vector to be like that. So in this update, the net input is now used against the true label, and here scaled by eta, and also here that is now direction and xi, and using this term it is updated. Now you can compare with the perceptron rule. In perceptron rule, here almost same. Now the difference is, okay, it is using now threshold the value, But here, that input is directly used, but this is the predicted one through thresholding. And also, the one more difference is that perceptron rule is using one data point at a time. But in Adaline, and by using this gradient descent technique, the summation of the such terms are used. So in each iteration, all the data should be accessed, and this total sum must be used for update. So that's the two major difference between perceptron and Adaline. Okay. Convergence and optimization issues with gradient descent methods. Okay. Depending on the choice of certain algorithmic parameters, the gradient descent method may fail to converge. For instance, if you choose eta large, then mostly it is divergent. You have to choose eta sufficiently small. And here, data characteristics often determines both successibility and speed of convergence, so that here data preparation or data preprocessing is very important to improve convergence. And for large-scale data, the gradient descent method is computationally expensive because it is the update is made through accessing all the data set, whole data set, so that it is expensive. A popular alternative is the stochastic gradient descent method. We'll deal with this one in part 1, and these two will be treated in the part 2 of the section. Here, for this portion, we consider here now hyperparameters. In machine learning, a hyperparameter is a parameter whose value is set before the learning process begins. So that is a kind of algorithmic parameter. For example, here the learning rate eta can be decided earlier. And also, you can decide the number of maximum iterations or maximum epochs and iter and earlier. Okay, here, once you choose eta and small, then the gradient method is converging toward the global minimum. But if you try to choose large eta, then it can be oscillatory and then blow up. Here, hyperparameters must be selected to optimize the learning process and to converge fast to the global minimizer and avoiding overfit. So for most cases, along with the gradient descent method, the learning rate eta must be chosen small. Okay, this is part 1. We'll continue in the second part. Thank you.